Okay, so here we see a guy, he's got a floor, right? And you can see that he's got a lot of different colors. And this is, we'll say this is just the floor of his room. And he decides he wants to paint his room. So he's got to figure out, the area of this room. So he can figure out how much paint goes in here, right? So he's going to, it's just, from the shape of it, you can see the shape of this here is just going to be like a rectangle, possibly a square, but we're just going to say it's a rectangle. So we're going to go length times width. Okay, that'll give me the area of the floor. Okay, so what happens is that he figures that out. He figures out the area of his floor, that it's length times width, and he gets the area. The next day he decides he doesn't like the color. So what he's going to do is he's gonna change the color. He's going to paint over it. So he gets more paint and he paints over it. Okay. Now the next day he paints a little bit more on top, and then every day after that he starts saying, "Oh my gosh, let me paint over it. Let me paint over it. Let me paint over it." And eventually that paint starts to kind of build up. Okay. So the paint starts to build up. So let's try and see what would happen. As he adds layers of paint, you can see that what's going on, the paint is building up. It's getting taller and taller and taller and taller. And pretty soon he fills his entire room up with paint. There's no way to get inside. Well, this is now not just, a layer of paint, but it's so many layers of paint that have gone in here. Every layer filling higher and higher and higher. Now we need to know how much total paint was used. Well, we have this original floor here, right? Here's the original floor. So we would say it's length times width. But now we've got to figure that out times this dimension too. That's a height. A length times a width times a height. We're going up into the third dimension. So this is first dimension, second dimension. There's the third dimension as we go up. Okay? And you can see that, to find that out, this is now what we call volume. This is no longer an area. The area was just the floor. But now that we've gone into the third dimension, we're calling that the volume. Okay? So how do we find the volume of what's inside here? Well, first of all, let's talk about this shape. It's a polygon on the bottom and a matching polygon on the top, and it just rises straight up. So this is what we call a prism. And so in this case, it's a rectangular prism. Okay. You also have, I've got another one here. Here's another one. This one is called a triangular prism. Okay. Why is it triangular? It's got a triangle for a base and a triangle for the top. So it's a triangular prism. Now let's look at this formula for this volume. It says volume is equal to the base times the height. So in other words, we're just going to calculate what is the area of the base and multiply by the height. So how much paint did he use to paint this triangle base? Then, how many layers high does that go? Paint for the base times the height. So the area of the base is equal to, because it's a triangle, 1/2 times base times height. Then multiply that by how tall this thing is. So we say, notice that there's a lower b and a lower h. We're talking about the height of the triangle. So like maybe this measurement from this vertex to the opposite side. Okay, that's the height. And then this could be the base right here. So that would give us the area of the base. But to get the volume of the prism, we have to multiply it by the height. So we find the area of the base, that'd be this part here. Capital B is this area, and capital H is the height. Lowercase b is the base of this little triangle, and lowercase h is the height of that triangle. So we can find the area of the base multiplied by the height. Well, think about that. If that's, if that's the formula for the area of a triangular prism, and this is the formula for the area of a rectangular prism, we find the area of the base, length times width, times the height. They're pretty much the same formula, right? Because we have the area of the base, how much paint would go in the base, and multiplied by the height. Right? And, if you adjust that, you're still going to use the same technique. You'd say, what is the length times the width to give me that base multiplied by the height? Won't really matter, right? Doesn't matter what shape that is, find the area of the base times the height. And that's for all prisms. Well, let's think about a cylinder here. I've got a cylinder here I want you to look at. Okay, cylinder, what's the difference between a cylinder and a prism? It's pretty much the same thing. The difference is that the cylinder has a circle for a base, not a polygon for a base, a circle for a base. So, you know, the circle can get bigger, right? It still has a circle as a base and a circle at the top, and then it just rises up to it, right? So that's a circle. So how would we find the formula for the volume of a cylinder? Well, again, here it is. The volume V is equal to the base area B times the height H. So again, we just find out how much paint would go on the floor here, and then think about how many layers of paint this guy's going to use, right, to fill that room all the way up, to keep going up. So the area of the base times the height. Yes, it's got a different formula for the area of the base because it's a circle. So instead of doing length times width, we're doing pi r squared. That gives us big B there, right? Then we're multiplying that by the height of the cylinder to give us the volume. So you can see here that the volume formulas for both a prism, which is just equal to base times height, and a cylinder, which is equal to base times height, area of the base times the height, is the same. We're just going to find the area of the base multiplied by the height. So they're basically the same, and that's the first part of what you kind of need to understand. There is a thing about that's called Cavaliers Principle. I want you to see this. What it says is that, you know, if this was stacked up, say this is a bunch of coins stacked on top of each other, kind of like this, okay? As you measure the slices of that area, right? So think of it as this is the paint that they painted on top. Even though it doesn't rise directly straight up, it's still going to have the same volume as long as the slices all measure the same. That's what it says. The result from calculus states that if two solids of equal altitude, so they have the same height, right? Oh boy, I shouldn't have done that. They have the same height, have identical cross-sectional areas. You can see the cross sections there. We slice across. Each slice makes a cross, right? Then the solids are going to have the same volume. As long as we have the same slices across, they're going to have the same volume. So we're going to talk about that momentarily. I'm going to pause here and show you some more stuff. Now, we remember that when we had the cylinder, we measured the area of the base, and then it rose straight up to a matching circle at the top. That's a cylinder, right? And it doesn't actually have to rise straight up. If it doesn't rise at a 90-degree angle, then it's just not called a right cylinder. It's called an oblique cylinder. So it kind of rises at an angle. And that's okay. Cavaliers' Principle says as long as the cross sections have the same area and the height is the same, it'll be the same volume. Okay? So, but this is for a cylinder. What about for a cone? Well, it turns out with a cone, we're going to adjust the height of the cone. We still have the base, the area of the base, right? So it's a circle for a base. And the difference between a cone and a cylinder is that it rises to a point. So the volume, all we're going to do is we're going to only take a third of the original volume. So we're eliminating 2/3 of the volume when we use this technique, okay? So we're basically just saying what is, you know, 1/3 of the volume of the cylinder. So we start with the area of a cylinder, so area of the base, or volume of a cylinder, area of the base times the height, then just multiply by 1/3, and that'll give us the volume. Doesn't matter as we change the radius or the height, it's the same technique, okay? What about with a pyramid? Well, with a pyramid, oh boy, we kind of got a funny looking pyramid here. Let's try adjusting the height. Let's try adjusting that base. There we go. This is a triangular pyramid. A pyramid is like a prism. It can have any shape base you want, and it rises to a point, much like a cone. Remember, the cone rises to a point, pyramid rises to a point. Just has a polygon for a base. So notice something funny here. What does the formula say? It says find the volume of, just like the volume of the prism. If we had a matching prism, it's the area of the base times the height. But in this case, you're going to multiply by 1/3. Okay, you're going to multiply it by 1/3. Because we are shaving away 2/3, right? That's basically what we're doing there. So you can see that won't matter we're going to have the same formula for the volume of a pyramid. 1/3 times the area of the base times the height. So these are two important things. Cones and pyramids, their formulas are related. 1/3 times the area of the base times the height. 1/3 times the area of the base times the height. Can you make the argument now that the formulas of a cone and a pyramid are basically the same thing? Find the area of the base times the height and then multiply by 1/3. See the relationship between the two? I hope so.